Hey guys, we are back with another video, and today we are going to talk about this particular research paper where they are saying particularly not all attention is needed. So from the name itself, it's pretty much clear that they are going to reduce some layers of attention. Maybe they are going to transform an entire formula of how attention is working. So that we are going to look at the paper, and the main line, what actually matters in a transformer is attention we all need, and can we reduce the things that are actually present there from previously and now we are adding something new. We'll see. So from the paper itself, they are saying that scaling transformer LLMs has demonstrated promising performance across various tasks, but it also introduces structures which are actually redundant. They are actually saying that word, so posing efficiency challenges for real world deployment. They're saying such as MLP attention layer is underexplored. Then MLP, they are, I think, definitely talking about the multi-layer perceptron thing, and which includes the blocks, MLP and attention layer using a similarity-based metric. Okay, so they are saying that they have investigated this whole redundancy part, which they are claiming, at least in the initial thing, that okay, this is sort of useless when it comes to few layers which can be removed, and we don't see degradation in the performance. So they say, despite the critical role of attention layer, we found that a large portion of these layers exhibit high similarity and can be pruned without degrading performance. Now, this is a very big claim, right? This is a very big claim because they are saying that they are removing some of the layers and they still don't see any degradation in the performance. So these numbers, we are going to talk about it in the results part. They are also saying that additionally, we further propose a method that jointly drops attention and MLP layers, allowing us to more aggressively drop additional layers. So same thing they have done, and they have achieved really good numbers. So the best part is they have made this code open source, so anyone can go and test this, because if this is holding true, then actually not all attention is needed, what there is claiming in the headline of the paper, right? So I'll take you guys to the main part. I'll try to keep the video as short as possible, because I know once the video crosses our 10-minute mark, usually it becomes a bit boring. So I'll try to keep things as simple and fast possible. So they're saying there are three particular terms, right, in transformer: the block, MLP and attention. So they're saying that we first apply a block drop approach, but observe that removing entire blocks lead to significant performance degradation. That is very obvious. This suggests we need a more fine-grained strategy, right? So they have done another analysis, and they say separate pruning of attention and MLP layers, not doing it for a particular block, but doing it for separately for MLP and then for attention. So this particular thing may work out. Instead of removing the whole block, they are going slowly for MLP, then for attention, right? So our findings reveal that dropping MLP layers negatively affect performance, a substantial proportion of attention layers also, right? The core of transformer architecture. So they for instance, dropping 50% of attention layers in Llama 270 billion results in comparable performance to the full model, indicating a high degree of redundancy in these layers. So the useless part which we're saying is actually present, if you see here, is present in this in these particular layer, right? This high degree of redundancy you see in the attention layer, right? The attention. So instead, if you see, these attention layers are highly similar, right? Highly similar. Now, coming back to the point that by building on these insights, joint layer drop, which targets both layers, right, MLP and attention, by combining importance scores of these layers. So I think we are going to, in summary, the contribution comes like this. They have, they are covering the three important parts, dropping all three: block, MLP and attention, and giving us an analysis. Then they introduce this attention drop. They also introduce this joint layer drop, where they are, targeting both attention and MLP layers. Now they are going one step ahead and giving us the results, which is 2.4% performance reduction while achieving up to 48.4% speed up. This is actually a good trade-off, because if you see, if we are only degrading by 2.4% and getting a 48.4% speed up, and most of the time we are working on specific tasks, right? Specific tasks. So it's fine, right? This much, I think, if we fine tune our model, we are anyways going to achieve. So yeah, it works. So now we are going to go to the related words, which they are saying the model compression. So we already know, right? We have already talked about pruning. We have talked about quantization. So I think they have mentioned all these things here. And LLMs can be compressed to promote their efficiency in memory and computation. right? They have quantization, then you have pruning, then you have widely most famous techniques. So yeah, our methods, they are saying block drop and layer drop focuses on removing structured modules rather than fine-grained parameters. So obviously, right now, what is the best method, right? We already know these two things, right? Where we remove parameters, right? So they are saying that instead of parameters, let's directly remove the structure modules, right? We are removing the whole modules. So you see the difference. This is a very huge difference. We were just removing some parameters using pruning and quantization. Now we are actually removing a whole module from the architecture. That's a huge thing, right? So yeah. Now, how do they do this? So they are saying we present the methodology for identifying and removing. I forgot to mark this. For identifying and removing redundant layers. Now, by beginning, they are saying we introduce a similarity-based metric to assess redundancy score across both attention and MLP layers. Okay, cool. So, coming to similarity-based drop, they are saying the underlying hypothesis is that redundant modules produce outputs that are similar to their inputs, right? Because suppose if I am telling you one thing, this is a layer, let's say L. Okay, now this is an input X. And you see that the difference in X that comes is Y, and Y is actually almost very similar to X. So what you can say, this is sort of useless. I'm not saying it's completely useless, not at all, but it is sort of useless because if you see that in another parameter, when this Y, let's say, is going to a layer L2, and then this is coming Z, and Z is somehow very much different. Like very much different than Y. So we can see, okay, some changes have been made, right? So on this hypothesis, this is just a hypothesis right now. They are saying we thought that they can, sort of remove those layers. So similarity between hidden states of X, input X and Y is quantified using cosine similarity. Simple as that, right? So if they have calculated the importance score, 1 minus the cosine similarity of X and Y. So models with higher cosine similarity exhibit lower importance score, indicating that this model is sort of useless. So you guys can remove this. So higher the S, you can say sort of higher the S, more is the useless. Okay, good. So, okay, fine. When I'm saying useless, please don't take it as complete useless thing. I am just trying to, create a synonym of redundancy. That's it. So block drop, we are saying that we first consider dropping entire blocks that are deemed unimportant. Similar thing they are doing, we compute the similarity between input and output for each block, and for Lth block the importance score is calculated as 1 minus the cosine similarity of block this X and block Y. Okay, so obviously the input and output of each block is taking the place. So let's say this is the input and this is the output, so we will have some that, and similar thing is going to happen. The higher is the similarity, we are going to drop that, right? So they have also shown the importance of these blocks. If you see the layer index, and from I think from figure 2, they are telling that transformer blocks operate sequentially with each block output feeding into the next to be valued. Obviously this is happening, right? We already know about the architecture. So the motivation coming to this, that this obviously block drop is an aggressive technique, because obviously you are removing the whole, you are not only removing one part, you are removing both MLP plus attention, right? You are removing both of these things from your system. This whole module you are removing itself, this whole block you are removing, right? So a transformer block consists of both layers. These layers perform distinct function, and these facilitate contextual information flow between tokens and MLP layer, transforming the token representation, giving their distinct roles. We access that redundancy of each layer separately by measuring the importance score of is important, right? So that is what they have done. In importance score of MLP layers, we use various calibration datasets for comprehensive analysis. These things I think you guys can go and read, because this layer indexing is obviously as deep as you go, you will find the difference, right? Now this MLP drop in the figure 4, they are saying each MLP layer is following a obviously layer normalization process and involves a residual connection, ensuring that the part of input is preserved in the final output. So given this input of the layer normalization before MLP, the output can be formulated as this, right? So similarly, the thing they are saying, since output contains both residual and MLP, evaluating similarly basis of MLP can be misleading, obviously, because the changes have been done here, right? We already see some changes here, right? So it's not so. To address this, we consider the MLP layer and its associated layer normalization as single unit and compute their importance score as following. So I think it was pretty clear that why they did that. and by treating this layer as a single entity, we ensure a more accurate measure of importance. Okay. Similarly, for attention drop, it also operates with residual, so they are doing the same thing here also. To address the same thing, they are taking it as the whole, single entity, so that it gives a better accuracy, right? Now they have this whole formula here. Now what they are saying here is, where X is the input of corresponding layer normalization and Y is the overall output, right? So now layer drop for both MLP is performed in one shot manner, calculating importance scores and removing redundant layers in one. Okay, good. Now the implementation and loading the prune model, after removing those layers, the prune model can be easily using existing libraries, Hugging Face transformers, we all know, right? Now coming to the next part, which is investigation of dropping different target modules. So the speed degradation part they have defined as this: the delta of average and the delta of speed up. This whole that difference that they are taking, that division that they are doing, that is going to depict that. And coming to the part, block and MLP layer, significant performance degradation with speed up. So block drop and MLP drop both lead to notable performance declines across modules despite achieving speed up. So the point is, if we have this whole graph, right? Now this is the speed up, let's say, and this is the accuracy. I think I should have done this differently. Yeah, I would say, let's say this is the accuracy. Okay, this is the accuracy, and this is the speed up. Okay. Now we always want if the speed up goes up, right, the accuracy should not go down, right? Let's say speed up is going up, accuracy should not go like this, right? We want at least some consistency here. Like a little bit should be okay, but a significant should not happen, right? So these results suggest what they're saying. While block and MLP drop do provide moderate, they do though at the cost of significant performance degradation, especially at higher drop ratios, and we don't want that, right? That now coming to this attention drop particular, right? Only attention drop, what they're achieving here, they are dropping all the layers, and they say maintain it's over 99% of original performance, Mistral 7 billion and Llama 2 13 billion. So these results demonstrate attention layers are highly redundant and their removal has minimal impact on model accuracy, making attention drop a highly efficient tuning strategy. Okay. Now results you can see here, because these are the method, the baseline, then the block they have dropped, block 4, block 8, MLP4, and you can see a significant decline here, right? If you see on the Llama 2 13 billion, from 59.9 it is going to 48. It's an around 12% decrease. But for attention, you can see attention 16 layers, right? You can see here only 3%, drop. Similarly, you can see for Mistral model also the same results. Now larger models show consistent robustness to attention drop. So if you see here, this is the Llama 3 8 billion and Llama 3 70 billion. Okay, Llama 3 70 billion 75.1 to 73.3. That is almost, if you compare both of these, this is almost 2.2%, I guess. Only 2.2% drop. That's it. And just see the number of attention layer that you have got, right? So it's a lot of difference, right? And when it comes to the dropping of layers, but obviously the main difference, it's very low. It's very low, right? So it's pretty clear that attention layers can be removed, and it shows not much difference in the the performance, and the number of the speed up is 1.4 times. So it's really good for us, right? Similarly, the efficiency of attention drop, they are saying we examine the reduction in memory ahead due to the key value cache. So the KV cache, I think you all guys know, we have this KV cache where we store things that we don't want to calculate again, and measure the speed up during the entire generation phase. So obviously this will also reduce the attention layers, right? And this leads to the reduction in memory, and we have already seen the speed measurement part. So I think the rest of the things are things that they are showing, that how the visualization of importance score, the visualization of dropping order, and most of the time you will see that for attention layer things work perfectly for us, right? So attention layer dropping works best for us. A block drop is not at all working. And for MLP, there should be a consideration, I would say. There should be a consideration that maybe we can improve this somehow in future, right? Because block drop is not at all working for us because we are removing both of the things. Even I would say MLP is not at all helping right now, but yeah, attention we can think. Okay. Now, yeah, that was it for this video. I think I've covered most of the things. I would request you guys to go and definitely read this paper from their website. I will pin this in the description as usual. And this paper is an awesome paper because it covers a lot of things, that what actually is needed in a transformer, what matters in a transformer. So yeah guys, that was it from my side. I hope you guys learned something new. So thank you and have a nice day.